Okay, so we'll resume now. Thank you very much for sticking around. So it's a big pleasure to present Philipp Reiser from the University of Freiburg. He's going to speak about positive intermediate Ricci curvature, surgery, and Gromov's Betti number bound. Thank you, Philipp.
Yeah, thank you for the introduction, and thank you very much for the invitation to speak. So the goal of this talk is to present a few construction techniques for metrics of positive intermediate Ricci curvature, and all of what follows is joint work with David Wraith. So first of all, let me introduce what intermediate Ricci curvatures are. So yeah, if we have a Riemannian manifold and a unit tension vector, then the Ricci curvature can be defined as an average of sectional curvatures, namely the average of all sectional curvatures of two planes that contain our vector V. So it's a different definition than Marco used in the lecture, but of course it's equivalent. And the idea for intermediate Ricci curvatures now is to, instead of taking the full average of all the two planes, we take a partial average. So that's the definition. So we fix a number k, which will be typically between 1 and n-1. And then we say the metric has positive kth intermediate Ricci curvature, and we will write it as Ricci k, like this. If for all unit tension vectors and now all orthonormal k frames in the orthogonal complement of the vector, this sum of sectional curvatures is positive. And simply from the definition, we see if we set k to 1, then we just have a single summand here, and then this condition just means we have positive sectional curvature. And similarly, if k is n-1, then we obtain the definition up here, and then we have positive Ricci curvature. And for k in between, we have a range of, one can say, interpolating curvature conditions from positive sectional curvature to positive Ricci curvature. And when k becomes bigger, this becomes a weaker condition. So Ricci k positive implies Ricci L positive if k is less than or equal than L. Okay, so these, yeah, one should say this is not the only intermediate Ricci curvature condition, and this is also a very confusing terminology. So there also exists k positive Ricci curvature or positive p curvature, and I'm not going to talk about these, so just consider these the intermediate kth intermediate Ricci curvatures. And yeah, these conditions have been around for some time already. So the earliest result I could find goes back to the 60s. And there are many results for positive Ricci or positive sectional that have in some way been extended to these intermediate conditions. For example, a very nice example is by Wu from 87, which says if we have a compact Riemannian manifold of positive Ricci k, such that the second fundamental form, the boundary, is k non-negative. By that I mean that the sum of the k smallest eigenvalues of the second fundamental form is non-negative. Then we have that M is a CW complex with only cells in dimensions at most k minus 1. And the nice fact of this result is that it connects two known results, namely one by Gromov from 69 for k equals 1. And in that case, it says if we have positive sectional curvature and the second fundamental form is positive semi-definite, then the manifold is contractible. And another result by Lawson from 70, which says if we have positive Ricci curvature and the mean curvature is non-negative on the boundary, then we have a CW structure with cells in dimension most n-2, or one could also say the inclusion of the boundary is unconnected. And yeah, so this result now nicely connects these two results and sort of gives an interpolating result. Yeah, this is one example, but there's one problem, namely that we only have very few examples of such manifolds. As you might know, the number of known examples for positive sectional curvature are extremely small. And for positive Ricci curvature, although there are still many open questions, we have way more examples in that case. But for Ricci K, as soon as K is strictly less than n-1, we are very much in the same as for positive sectional curvature. So the number of examples is quite small. And so the biggest source of examples so far is by Arman Costare and Domínguez Vázquez, González Álvaro, and Moyer, where they considered homogeneous spaces and extended, one can say they extended techniques from positive sectional curvature to positive Ricci K. So in particular, they considered matrix with large symmetries and then got quite a few more examples than one has for positive sectional curvature in that way. And the approach we will take now is sort of opposite. So we start with positive Ricci curvature, and we want to extend these results from there into Ricci K positive. There, typically, K will be large. And what I also want to advertise is that there exists a full list of books, articles, and preprints that contain anything about Ricci K positive, and it's on the website of Lawrence Moyer. And at least for me, it has been very helpful, and I want to advertise this a bit. Okay, so before we can generalize these results for positive Ricci, let me actually tell you what these techniques for positive Ricci are. So let's start with Riemannian submersions. So given a Riemannian submersion, we can always split the tangent bundle of M here into a vertical part and a horizontal part. So the vertical part is the kernel of the differential of the projection, and the horizontal part is then just your orthogonal complement. So on the vertical part, everything gets mapped to 0, and on the horizontal part, the differential is an isometry. And now, given this, we can now modify the given metric G by a parameter T. Namely, on the vertical part, we scale the metric by T. And on the horizontal part, we leave it as it was. And we also want the horizontal part stay orthogonal. And this metric is also called the canonical variation. And some further notation. So for a point in the base, you denote by this the fiber over this point, so the preimage on the pi, and by G hat, the corresponding induced metric. And if we assume that the submersion has totally geodesic fibers, then all these fiber metrics isometric, and we can just drop the base point. And then we have the following theorem. It's a very well-known theorem, and it's also not too hard to prove. And I think it's been known for a long time, so I don't know how to attribute it to. It says if we have a Riemannian submersion with totally geodesic fibers, where everything is compact, and where both the base metric and the fiber metric have positive Ricci curvature, then the canonical variation will also have positive Ricci curvature if we make this T small. So we shrink the fibers, and if we make this small enough, then we will have positive Ricci curvature on the whole space. And if we want to, like a corollary of this, if we want to apply this to fiber bundles, I think this has also been known for a long time. First place where I could find this is in the book by Gromov, and preliminary versions of this are due to Poor and Nash. And it says if we have fiber bundles, so here we do not fix metrics yet, just topologically a fiber bundle with fiber F and structure group G, and everything's compact. Then if we assume that the base has a metric of a positive Ricci curvature and the fiber has a G invariant metric of positive Ricci curvature, then we can put a metric of positive Ricci curvature on the total space. So this is a way to lift positive Ricci curvature in a fiber bundle from the base to the total space. And in particular, the case we will consider is we have a linear sphere bundle, so the fiber is a sphere and the structure group is just the orthogonal group. And then we can always lift from the positive Ricci curvature from the base to the total space. So let's first focus on this theorem for Riemannian submersions. And to get an idea what we could expect for a positive intermediate Ricci curvature, let's consider first a very simple case, namely that we have a Riemannian product. So M is the product of M1 and M2, and the metric is also a product. So and then we get easily a Riemannian submersion just by projecting on one of the two factors. Then we fix the smallest values for which we have Ricci K1 positive on G1 and Ricci K2 positive on G2. Now the question is, for what K do we have Ricci K on M? So let's start with a vector tangent to M1, and we extend it to an orthonormal L+1 frame for some number L, so that this whole frame is tangent to the first vector, and we take a full orthonormal basis in the second vector. So in this way, then we obtain an orthonormal L plus P plus 1 frame in the product. And then we consider the sum of sectional curvatures. And the key observation here is that if we have a sectional curvature, like a mixed sectional curvature, spanned by a two-plane of vectors tangent to M1 and tangent to M2, then the sectional curvature just vanishes. So this holds for all these vectors tangent to M2. So in fact, this sum is just a sum up to L. So just for this orthonormal L+1 frame. So we are entirely in the first vector. And then since K1 is chosen to be the smallest value for which we have Ricci K1 positive, this would in general only be positive if L is also at least K1. So this means that the product cannot have Ricci K positive if K is less than P plus K1. And we can do exactly the same thing by reversing the roles of the two factors. And then we also see that we need that K is at least Q plus K2. So we have two conditions on K, and it turns out that this is also sufficient. So the product has positive Ricci K if and only if K is at least the maximum of K1 plus P and K2 plus Q. Yeah, we'll see actually later a proof of this in a more general setting. Yeah, and note this is always above the middle dimension, but we can get as close as we want if P and Q are close. Okay, so this is what you have for products. And now the theorem we have is the following. So given a Riemannian submersion with totally geodesic fibers, again, everything compact. And then if we have a metric of positive Ricci K1 on the base and positive Ricci K2 on the fiber, so that exactly this condition is satisfied, then again, the canonical variation has positive Ricci K for all T sufficiently small. So in some sense, we get the best possible value for K here. And as I said, this is always above the middle dimension. Okay. And as for positive Ricci curvature, we get as a corollary for fiber bundles. If we have a fiber bundle with fiber F and structure G, again, everything compact. And then if we have a metric of positive Ricci K1 on the base and the G invariant metric of Ricci K2 on the fiber, then the total space also its metric with Ricci K positive for every K at least a maximum of K1 plus P and K2 plus Q. So let's consider the theorem first. So how do we prove this? I also want to say this result is both optimal and not optimal. So it's optimal in the sense that in a general setting, K cannot be chosen smaller simply by this observation from where we consider products. But it's also not optimal that saying that in certain situations, K can actually be smaller. For example, in the context of fat bundles, and yeah, if one chooses the metric in the right way, one can actually get Ricci K positive for smaller K. Okay, now let's consider the proof of the theorem. So for that, I need to introduce a new operator. So for a Riemannian manifold, if R is the Riemann curvature tensor, then we define this linear map on each tangent space, which is just given for a fixed tangent vector by inserting this vector in the second and third argument of the curvature tensor and yeah, leaving the first argument free, so we get a linear map. This is also sometimes called the Jacobi operator. And then if we take an eigenvector of the orthogonal complement of this map with some eigenvalue lambda, then lambda will be just the inner product of RV of W with W. But at least if V is also a unit vector, then this is nothing but the sectional curvature of the two planes spanned by V and W. So we see if we sum over eigenvalues of this operator, we end up with a sum of sectional curvatures, as we saw in the definition of kth intermediate Ricci curvature. And yeah, we also have that V is an eigenvalue and the eigenvalue, an eigenvector with eigenvalue 0. And then we can characterize this condition by saying it has positive Ricci K if and only if the sum of any K eigenvalues of this operator when we restrict to the orthogonal complement is positive for all unit vectors. And if we want to consider this map on the full tangent space, then we have to add also this eigenvalue 0. And then we get that the sum of any K plus 1 eigenvalues of the operator is positive. And yeah, this is quite useful because simply considering the definition here is it's very difficult to deal with it because one has to consider all these unit vectors and all these orthonormal K frames. And yeah, this is very difficult to deal with. And this is a much nicer condition. We only need to fix a tangent vector, and then we only need to consider eigenvalues. And this is what we will use. Now we're back to Riemannian submersions. So if we have a tangent vector in the Riemannian submersion, we can always just split it into the vertical part and the horizontal part in this way. And then one can just simply compute this map RV, so the Jacobi operator for this V, in terms of the splitting into vertical and horizontal part. Then we get this 2 by 2 matrix. So we get here the Jacobi operator of the fiber and the Jacobi operator of the base. And this is scaled by lambda squared over t and mu squared. And when we get a lot of terms, but they tend to 0 as t goes to 0 or as go to 0 as lambda goes to 0. Now considering this, let's first set lambda equal to 0. And all these terms, this term vanishes, also the Jacobi operator and the fiber vanishes, and we are left with this matrix. And now if t is 0, also all these terms vanish. So we end up with a matrix with a big 0 block here, here, and here, and just the Jacobi operator of the base over here. And then we can use continuity of the eigenvalues. If t is sufficiently small, the sum of any p plus k1 plus 1 eigenvalues of this matrix is positive, because we have p 0 eigenvalues here and then we need the sum of any k1 plus 1 eigenvalues here to make it positive. So we get overall this sum. And now we again use continuity and extend it for small but non-zero values of lambda as well. So now if lambda is bounded from below by this value, then this time we make use of the Jacobi operator of the fiber. So we see that as t goes to 0, this term blows up. Or we can also equivalently just multiply the whole thing by t. So everything goes to 0 as t goes to 0, only this term remains. And then in a similar way, we can argue that for t small, the sum of any now q, which is the dimension of this block, plus k2 plus 1, which is the condition for this Jacobi operator, of the sum of any q plus k2 plus 1 eigenvalues of this matrix is positive. And this now covers all cases. And then we use the lemma and obtain that we have Ricci k positive for all k at least a maximum of p plus k1 and q plus k2. Okay, this is the proof of the theorem. And now for the corollary, it's not much we have to show once we have the theorem. So how do we get a metric on M, on the total space? So in this setting, we do not start with a metric on the total space, but we can still define the vertical part simply by defining it as the kernel of the differential of the projection. And now we choose any horizontal distribution. So that means just any subbundle of the tension bundle that is complementary to the vertical part at every point. And in this way, then, so we can identify then the vertical part with the tension bundle of each fiber. So this is unique up to the action of the structure group. And but since the metric on the fiber is invariant under the action of the structure group, we can just set the metric on the vertical part as G hat. And on the horizontal part, we can then define it as the pullback of the base metric. And again, we require that the vertical and horizontal part are orthogonal to each other. And in this way, we obtain a submersion metric with totally geodesic fibers in M. And then we simply use the theorem, which tells us that for t sufficiently small, the canonical variation of this metric has positive Ricci k for this lower bound for k. Yeah. And we see in this proof that this just works for any choice of horizontal distribution. And as I said before, in a specific case, where we choose this in a nice way, we can actually get a better value for k. But for the applications we have in mind, which are surgery, we actually need that we are able to choose this horizontal distribution freely. So for our case, this is all we can get for k. Okay, so in this way, we can lift metrics of positive Ricci k along the fiber bundles. And one application I would like to discuss is surgery. So, yeah, maybe you're familiar with surgery. We do not want to consider surgery in a very general case, but we want to consider a very specific surgery operation, which is defined as follows. So given two linear sphere bundles, so this is the first one. So we assume that the base is a sphere here. So here we have base the q plus 1 sphere and fiber the p sphere. And for the other sphere bundle, we want the dimensions to be swapped in the sense that the base is the p plus 1 sphere and the fiber is the q sphere. And then if we have embedded disks in each fiber, so for now it doesn't matter how we embed them, just some embedded disks. we know that since disks are contractible, the bundle will be trivial over the disks. So we can just identify them with products. So for the first one, we have the Q+1 disk plus the P sphere, and here we have the P+1 disk plus the Q sphere. And now the important observation is that the boundary of these two parts is the same. Namely, here we got the Q sphere across the P sphere, and here we get the P sphere across the Q sphere, which is the same after just interchanging the factors. And we use this by defining a new manifold. Namely, we cut out these parts of the bundle, and then we use that the boundaries we get are the same, namely the P sphere plus the Q sphere, and then we just glue these parts together. And in this way, yeah, the fiber of the one bundle gets glued to the base of the other bundle and vice versa. And in case you're familiar with it, this is simply the effect to the boundary of a plumbing operation. If you've not heard of it, then just think of this. Yeah, so this is what we can do for two given sphere bundles. But of course, we can also do this to several sphere bundles, and we can do this several times, this gluing operation. And this gluing information can be stored in a graph where each vertex is in the linear sphere bundle over a sphere, and each edge then corresponds to a gluing operation in this sense. And for all this to make sense, of course, the dimensions have to match, as in this case. So in this way, from every graph, we obtain a manifold. The theorem now is, if a manifold is obtained by such a graph, and if this graph is simply connected and these numbers of P and Q are at least 2, then we can define a metric of positive Ricci K in this manifold for all K at least a maximum of P and Q plus 2. So the proof idea is as follows. So we already know that we can put metrics of positive Ricci K on each bundle, but now we need to consider the gluing and define a suitable metric so that we can glue these together. So we consider a single gluing operation. So for the first bundle, we require this embedded disk to be a small geodesic ball. And for the second bundle, we require it to be a large geodesic ball and should be so large that it contains a full hemisphere. And the reason is that for the first bundle is the one where we consider where all the bundles are glued to, like the second one. So we possibly need to take a lot of embedded disks here, so they have to be very small so that all those fit into the sphere. And yeah, now as before, we equip these the total spaces with submersion metrics, where the fibers are simply the fiber metric is just a round sphere, the round metric on the sphere, and we want the fibers to be totally geodesic. And we say the radii are R1 and R2. And the horizontal distribution is chosen in such a way that it is integrable over the disks. So it means it's according to the product structure we have there. And then the resulting metric will be simply a product metric over these parts. In particular, over the boundary, which is the part where we glue, it will be a product metric of 2 round spheres. Of course, the radii of these spheres can be different, so it's not clear that on the boundaries the 2 metrics are isometric, but they're at least somewhat close to each other. So they're both product metrics of round spheres. And from what we had before, we have positive Ricci K for these metrics, if K is at least a maximum of P and Q plus 2. But yeah, the problem is now, how do we glue these together? But even if they were isometric on the boundaries, the resulting metric would not be smooth in general, because we also need to consider the derivatives of the metric in normal direction of the boundary. And in order to solve this, we insert a cylinder in between here, which gives us some space to transition from one metric to the other. And we do this by what's called a W-bar product metric. So on each slice, we want a product of two round metrics. And as we walk through the interval, we want to scale these spheres by two functions, which we denote here by H and F. And now we have two conditions for this metric. So first, it should glue smoothly with the given metrics we already have for E1 and E2. And it should have positive Ricci K. And if we translate this for the functions, this means they should satisfy a system of boundary conditions in order to glue smoothly, and they should satisfy a system of differential inequalities on the interior to have positive Ricci K. And yeah, I don't want to go into too much detail here, but this is both of these are non-trivial. So first, at least for us, it was surprisingly difficult to actually decide when such a metric has positive Ricci K. But at the end, we arrived at the system of differential inequalities here. And then one also needs to construct these functions, which is also not obvious how one should do this. But yeah, so there we use some functions from some constructions for positive Ricci curvature that already works. And in this way, with the right choice of functions, we can then glue these together and obtain then a smooth metric of positive Ricci K on this glued space. And then we simply iterate this construction for the whole graph, for every gluing, and get a smooth metric on the whole manifold. Okay, so one application of this gluing operation is the following. So we can construct connected sums in this way. Namely, if we have a finite number of linear SP bundles over SQ plus 1, then the connected sum admits a metric of Ricci K positive, where K satisfies this lower bound from before. And the proof is by defining a suitable graph. Namely, one can show that if we take this graph, so here we take all these bundles, and in between we insert a piece like this, where we have here the trivial SQ bundle over SP plus 1, and here the trivial SP bundle over SQ plus 1. Then one can show that the space we obtain in the space simply the connected sum of these bundles. So it's not hard to show that a piece like this with these two trivial bundles just gives the standard sphere. And then one can use this to show that inserting these pieces just, that the effect is a connected sum operation of these bundles. And then by the theorem from before, we get a metric of positive Ricci K on this connected sum. And now we can use this to, in view of a very well-known theorem by Gromov, which says that if we have a metric or given an n-dimensional Riemannian manifold of non-negative sectional curvature, so non-negative Ricci 1, then the total Betti number of this manifold is bounded by a constant which only depends on a dimension. So this holds for positive Ricci 1. It's known that it does not hold for positive Ricci, so positive Ricci n minus 1. And now we're using this corollary. We can show that it also does not hold for every k which is slightly above the middle dimension. So the integer part of n over 2 plus 2. And yeah, given this corollary, it's not hard to prove. So we simply take trivial bundles, so a product of a p sphere and a q plus 1 sphere. And then the corollary says we have Ricci k positive for k at least the maximum of p plus q plus 2 on the connected sum of these products. And then if n is even, we simply take p as n over 2 and q as n over 2 minus 1. And then if n is odd, then we take P equals to Q equals to n minus 1 over 2. And then we get a metric of positive Ricci K on these spaces, and note that this L can be any finite number. And if we make it simply large enough, we get arbitrarily large Betti numbers for these manifolds, showing that there cannot be a Betti number bound as in Gromov theorem. And yeah, one could also say for K smaller, it's completely open if one has a Betti number bound. And this is, I think, a very interesting question, especially for K below the middle dimension. And another application we can consider are highly connected manifolds. So we have the following manifolds with the metric of positive Ricci K. So first, every homotopy sphere that bounds a parallelizable manifold for K, again, slightly above the middle dimension. So these subclass of homotopy spheres is a well-studied subclass, and one can show they only exist in odd dimensions. And in particular, dimension 7 and in dimension 11, all homotopy spheres are of this form. So this applies in these dimensions to all homotopy spheres. But in this dimension, we can say even more, namely every 2 connected 7 manifold has a metric of Ricci 5 positive, and every 4 connected 11 manifold has a metric of Ricci 7 positive. And for even dimension, we can also consider exotic spheres, and this time they will not be of this form. For example, the unique exotic 8 sphere has a metric of Ricci 6 positive, and the unique exotic 16 sphere has a metric of Ricci 10 positive. And the proof of this is now quite easy, given some very strong topological results, which say that all these manifolds are obtained by such a graph as I described before, which is simply connected. So for these homotopy spheres, if M is odd, then these are the so-called curvature spheres, and then you simply need a graph with 2 vertices and 1 edge. If M is even, then one can start with an E8 graph to get one of those, to get a generator of this subgroup, and then sort of connect them by connected sums, as we saw in the other application, to get all of them. This was shown by Wraith. And for these 2 connected 7 manifolds and 4 connected 11 manifolds, it was shown by Crowley and Wraith, that they can always be constructed by such a simply connected graph. And in particular, in this way, we can also construct very large Betti numbers. So the middle homology group can be any finally generated abelian group in this case. And finally, I want to mention an application to moduli spaces. So given a closed manifold, we first define the space of all Riemannian metrics on M that have a metric of Ricci K positive for some fixed K. Well, for now, this is just a set, but by taking topology of smooth conversions, we can turn this into a topological space. And on the space, we have an action of the diffeomorphism group, which is just given by pulling back metrics. And then we can quotient out this action, and this is then called the moduli space. And this can be thought of as the space of geometries of positive Ricci K on M. Simply because metrics are identified if they are isometric. So if they sort of define the same geometry on M. Then the result is the following. So we take a few of the manifolds we had before. So in the first case, we take the homotopy spheres that bound parallelizable manifolds in dimension 4 and -1. In the second case, we can take all the 2 connected 7 manifolds, where the first Pontryagin class is a torsion element, or we take any of the 4 connected 11 manifolds. And then the statement is that the moduli space for this manifold is an infinite number of path components. So how do we prove this? So here's a rough proof sketch. So this was known for causal Ricci, was shown by David Wraith. And yeah, so this construction of these manifolds via a graph at the same time also provides a manifold W whose boundary is M. So again, if you're familiar, this is then obtained by plumbing. And one can now take this metric we have on M and extend it over this manifold W. But it's not clear if we can preserve positive Ricci K, but at least we can have positive scalar curvature on the interior. And yeah, after deformation, we can do that. And now we calculate the Brecht-Stolz S invariant of this new metric. So this is an invariant of path components of the moduli space. So it takes a component and just assigns a real number. And in this specific case, so if this W is parallelizable, then there's a very easy formula for this, and it can simply be expressed in terms of dimension and the signature of W. And now, yeah, for this given M, now we find infinitely many graphs that define this manifold, and this in turn gives infinitely many manifolds W whose boundary is M. In particular, the signatures of these manifolds should be different. And then we have pairwise different S invariants for these. And therefore, since these are invariants of path components, all the metrics we get are in different path components of the moduli space of metrics of positive scalar curvature. And since inside this moduli space for positive scalar curvature, there sits the moduli space of positive Ricci K metrics, we also get an infinite number of path components for this moduli space. Yeah, so that's the proof, and that's all I want to say. Thank you very much.
Thank you very much, Philipp. Are there any questions either on Zoom or in the audience here? Not, I have a couple of, yeah, okay, there's a question here.
Hi, thank you, Philip. I have a question about the bounds on the Betti numbers. You said that you construct a sequence of manifolds having the sum of Betti numbers going to infinite, but I was wondering if is it possible to have a bound not in the same way that Gromov did, put it a constant, but also putting in a constant times something to control this divergence. I don't know if I was clear. Maybe it is this constant times something that a volume or something like that that may control the Betti numbers or something like that.
Yeah, that could be. We cannot exclude that. Yeah, that's actually an interesting point. So we only showed that, yeah, Gromov's Betti number only this sense.
But not, you didn't have an estimate on the asymptotics, no, right?
On which asymptotics?
Yeah, and the last part you said that as L goes to infinite, we have that the sum of these Betti numbers goes to infinite. But do you have a kind of estimate of the asymptotics of this sequence? Maybe they grow in an exponential way or something like that?
The Betti numbers itself grow linearly. And yes. Okay. But in terms of volume, so the construction is in such a way, if we add more summons, then the summons we add are sort of get smaller and smaller. So the volume will probably not blow up.
Maybe maybe another thing related with the manifold could control everything. I don't know.
Yeah, maybe. So we only show that this classical Betti number bound does not hold. What's also an interesting point is that what could be true is that one has like a partial Betti number bound. So this is known for positive Ricci, that the first Betti number is bounded. And one could have that if one goes further away from positive Ricci, one gets like the first, I don't know, if one has positive Ricci n minus k, that the first k Betti numbers are bounded or something like this. This would also be in line with what we showed there. So these manifolds all satisfy this.
Okay. So thank you. We have another question.
Hi, thank you, Philipp, for your talk. I was wondering if you have thought about this theory in the context of collapsing, because to me, it sounds like the K curvature, it's kind of like ignoring certain directions that you can, probably in some sense, collapse and get honest Ricci bounds.
Yeah, so what is true is that so if yeah, I don't know how this relates to your question, but if you have let's say a fiber bundle and you have positive Ricci K on the total space, and say total geodesic fibers, and then you project it down, then you have positive Ricci K for the same K. So this is preserved. So you sort of collapse the fibers. So you collapse the, and if then the K is a dimension -1 of the base, you sort of collapse the directions that are too much, and you get positive Ricci on the base. And yeah, I don't know, in a general setting where you have just a collapsing sequence, I don't know if this is known, but I would expect something like this is true.
Yeah, and actually even in this setup where you have like homotopy spheres bounding parallelizable manifolds, probably you could collapse since the thing that you bound is parallelizable, you can speak about global directions that you can collapse on this bounding, well, on the thing that bounds. Does that make sense?
I'm not sure if I understood. So you have a bounding manifold, and then
yeah, I mean you mentioned that you had like homotopy spheres that bound parallelizable manifolds.
Yes.
And I'm thinking more about collapsing directions on that parallelizable manifold, so you can get like bounds on the Ricci curvature, not only on the K Ricci curvature.
So you would get like a smaller dimensional object and have positive Ricci there. Yeah, I haven't thought about this, but yeah, that sounds like a good idea.
Okay, cool.
Thank you.
Okay, I have a quick question, I guess. So is something known, for example, for group actions? I guess like so fiber bundles, you have the same fiber, right? But for example, for group actions, can you lift K Ricci positive curvature, or is this known in some cases, or?
So lifting in what sense? So you have
so if you have
a quotient, or
yep, if you have like Ricci K positive, can you lift it somehow?
Yeah, so yeah, if the action is free at least, so that the quotient is a manifold, then this result here would also give you something on the total space.
Yeah, I see. Yeah,
and but yeah, it depends on what K you have on the group itself. And so this gives you something which is always then above the middle dimension, and in this, what I mentioned at the very beginning, in the this work by Dominguez Vasquez, Gonzalez Salvador, and Mouillet, they consider special cases of where you have homogeneous fibrations. And then you can even get better values for K in some cases.
Yeah, actually, on the topic of homogeneous spaces, so if I remember correctly, for example, for homogeneous spaces, it's equivalent to say you have Ricci, positive Ricci curvature than to have a finite fundamental group, right? I think that's maybe due to Verostovsky, if I remember correctly. So is there any like a topological obstruction for homogeneous spaces for kth Ricci curvature?
So yeah, you can do a similar thing, and because there you're in the easier situation where you have non-negative sectional curvature, so it's easier to characterize this condition. And then I think, yeah, it's a condition on the centralizer of the Lie algebra, and also in the same paper here they show that Ricci, they get this is again for positive Ricci, that it's equivalent to splitting off isometrically in S2. But for smaller values of K, I'm not aware of any purely topological parallelization. That would be actually very interesting. So also in general, there's no topological obstruction known for these that does not already come from positive Ricci.
Right. I see. That's very interesting. Thank you. So
Thank you.
Is there any more quick questions? Okay. Yeah, there's one.
Sorry, Raul again. Probably adding to Chucho's comment is the fact that there is this more or less general technique of using spin geometry and this how to say, what is the name? Well, this relation between the Dirac operator and the curvatures, different types of curvatures, and this, at least in the setting of scalar curvature, gives you some topological obstructions, right?
Yes.
So have you thought about this, I mean, extending in this direction, these K-Ricci curvature bounds?
I would say anything of this form for these would be very interesting, but if something like this works for positive Ricci is not even known. So here, in the case of positive Ricci, we don't even know if one can do anything like that. So there's a conjecture which is called the Witten conjecture, which is open for more than 20 years now, which would give an additional obstruction in this by using index theory of this type, but it's open. And so for the stricter condition, yeah, we don't know as well. But that's actually a very interesting question.
Right, awesome. Thank you very much, Philipp. So let's thank Philipp again.
Thank you.